When a learner tackles a highly complex problem, they eventually hit an invisible cognitive wall. The mental machinery locks up. But with the right intervention at precisely the right millisecond, an external system catches the friction, self-corrects, and the learner resumes motion. This portrait shows Lev Vygotsky, the psychologist who mapped this exact cognitive boundary. He called it the zone of proximal development, the specific space between what a student can do independently and what they can achieve with targeted guidance. Successfully navigating a learner through this zone has traditionally required a strict one-to-one ratio. An expert tutor sits with the student, monitoring their micro-actions and providing real-time, personalized prompts to keep them moving forward. The mathematical bottleneck here is absolute. Sustaining that one-to-one ratio across a classroom of 30 students, let alone an entire educational system, exhausts educator bandwidth. It is physically impossible to provide simultaneous, individualized scaffolding to everyone. The first generation of EdTech attempted to solve this scale problem by delivering static digital content. We digitized textbooks and recorded lectures, operating on the assumption that mass access to information would equate to mass learning. Those static environments generated mere procedural compliance. Students clicked through modules and memorized isolated facts, but without dynamic, responsive feedback, they rarely achieved true conceptual mastery of complex material. For advanced educators classified as pioneers in the DigComp-Edu framework, the objective evolves. They engineer digital architectures that actively sustain higher-order thinking. True scalability requires abandoning passive knowledge transfer. We must build dynamic, systemic intervention architectures that automatically provide missing expert guidance without requiring the continuous presence of a human teacher. The first half of this solution is algorithmic, artificial intelligence-driven, intelligent tutoring systems. The second half of the solution is social, computer-supported collaborative inquiry learning networks. This diagram illustrates how these two frameworks function differently but complement each other as the dual pillars of modern scaffolding. To the left, an algorithmic hierarchy analyzes data. To the right, a mesh network facilitates social interaction. The learner sits at the center. Advanced instructional design requires both subsystems to operate concurrently. The algorithmic and social layers wrap around the user, adapting in real time. This dual architecture replaces the traditional model of a singular teacher acting as the sole feedback bottleneck. The educator's role transitions into an architect of the environment itself, setting the operational parameters of the system. Integrating intelligent tutoring algorithms with collaborative inquiry networks creates a highly responsive, automated safety net. It mathematically mimics one-to-one expert scaffolding at mass scale. Let's look deep into the algorithmic layer. An intelligent tutoring system begins by mapping a standard curriculum into a machine-readable format. The engine driving this adaptivity is called knowledge space modeling. This network graph visualizes knowledge space modeling. It breaks abstract subjects into knowledge components. When a student errs, the system flags that node, calculates mastery probabilities factoring in response times, and if mastery drops below a threshold, instantly deploys a targeted intervention. These interventions take the form of automated system wizards, minimal fix units, or adaptive explanations designed to correct the precise misconception. This graphic maps AI vectors utilized during an intervention. We see peripheral elements like real-time feedback channeling directly out of the central AI node. The system uses these vectors to dynamically adjust difficulty without simply providing the correct answer. The algorithm's explicit goal is modifying the complexity just enough to keep the student actively engaged. It provides hints or steps back to prior knowledge, deliberately ensuring that the student still performs the required cognitive labor. Algorithmic adaptivity mathematically sustains the zone of proximal development. It engineers productive friction, forcing active problem solving rather than passive consumption. The algorithmic layer handles the data, but the social layer, computer-supported collaborative learning, handles the human meaning-making. This topology represents the collaborative architecture. Technology acts as an invisible mediator, routing data packets between student nodes to facilitate interaction. Connecting over digital artifacts like shared canvases, if student A constructs a failing model, the system automatically routes it to student B for review. In this specific architectural context, peer assessment operates as a highly rigorous scaffolding protocol. It is completely decoupled from evaluative grading. By forcing students to analyze and debug each other's work, the architecture effectively distributes the cognitive load across the entire network. The platform structures dialogic interaction. Students must negotiate terminology and defend their reasoning, forcing intersubjective meaning-making. In practical terms, this means peers use structured digital rubrics to verify each other's scientific hypotheses or double-check incoming inputs. This specific mechanism effectively turns every individual student into a dynamic, real-time scaffolding node for their classmates, drastically multiplying feedback loops. The students support each other, drastically increasing guidance without increasing the primary educator's workload. However, these advanced architectures carry a specific structural risk, the metacognitive trap, triggered by overscaffolding. When system wizards are too rigidly linear, or AI prompts become overly directive, they guide the student too closely through the material. Look at this self-assembling puzzle. It moves perfectly and rapidly, but it requires no human input. This sterile, frictionless execution illustrates what happens to learners. Over-automation degrades their metacognitive control, crippling their ability to plan, monitor, and evaluate their own strategies. True pedagogical design requires the opposite. The system must force the development of heuristic strategies, where the student figures out how to solve the problem. To achieve this, optimal scaffolding architectures are deliberately programmed to withhold complete solutions. They provide just enough support to prevent frustration, and no more. Maintaining that precise level of cognitive friction is essential. The struggle to bridge the final gap is what triggers deep conceptual reorganization. Effective digital environments carefully calibrate their support. They force learners to actively manage their own problem-solving processes, ensuring the human brain does the heavy lifting. This unified three-dimensional diagram represents a standard for modern educational innovation, the concurrent integration of social CSCL networks and algorithmic tutoring. In this combined model, the zone of proximal development is no longer a static circle. It is a fluid, pulsing boundary that dynamically reshapes itself based on real-time data inputs from both the social and algorithmic layers. The algorithmic layer continuously handles precision tracking and difficulty scaling, while the social layer simultaneously drives complex meaning-making and dialogic interaction. When this complex scaffolding structure is architected correctly, the mechanics disappear. The underlying technology remains entirely invisible to the learner using it. The resulting experience for the learner is one of seamless, self-regulated autonomy. They navigate complex problems feeling fully in control, unaware of the safety nets catching them when they slip. This shift completely redefines the DigComp-Edu pioneer. Reaching the highest levels of digital pedagogy requires educators to act as systems architects, designing the environments where learning occurs. This requires taking the principles of educational psychology and mastering their algorithmic operationalization. Effective educational technology calibrates cognitive load with precision, making the highest levels of intellectual complexity accessible to every learner.